My dear students, welcome back to our channel. In this video, I will be explaining the BCA third semester subject operating system concepts as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: what is process synchronization? Process synchronization is a way for the operating system, OS, to make sure that multiple processes can run at the same time without interfering with each other, especially when they share resources like memory, files, or printers. Without synchronization, processes may overwrite each other's data or produce incorrect results. Example: imagine two people editing the same Google Doc simultaneously. Without synchronization, one person's changes might overwrite the other's work. With synchronization, like track changes, both can work safely without conflicts. In computers, synchronization is important when processes enter the critical section, the part of code where they access shared resources. The OS ensures that only one process accesses the shared resource at a time. Key points: prevents data inconsistency, ensures safe execution of concurrent processes, achieved using Mutex locks, semaphores, and monitors. In short, process synchronization is the OS technique to coordinate multiple processes so they run safely and efficiently, avoiding errors and conflicts. Next important short question is: 2. Define Mutex locks. A Mutex, mutual exclusion, lock is a mechanism used by the operating system, OS, to ensure that only one process can access a shared resource at a time. It prevents multiple processes from entering the critical section simultaneously, avoiding conflicts and data corruption. How it works: a process must acquire the Mutex lock before entering the critical section. After finishing, it releases the lock, allowing other processes to enter. Example: imagine a single ATM machine shared by many people. A person, process, must wait their turn, acquire the lock, to use the ATM. Once done, the next person can use it, release the lock. Key points: ensures mutual exclusion for shared resources. Simple and widely used for process synchronization. Helps prevent race conditions where two processes try to modify the same data at the same time. In short, a Mutex lock is like a key that allows one process at a time to safely use a shared resource, keeping the system reliable and error-free. Next important short question is: 3. What is semaphore with example? What is semaphore? A semaphore is a special variable or abstract data type used by the operating system, OS, to control access to shared resources by multiple processes. It helps in process synchronization and prevents race conditions or conflicts when several processes try to use the same resource. There are two types of semaphores. 1. Binary semaphore works like a Mutex lock, 0 or 1, allowing only one process at a time. 2. Counting semaphore can allow multiple processes to access a resource up to a set limit. Example: imagine a parking lot with 5 spaces, counting semaphore is equal to 5. Cars, processes, enter if a space is available and decrease the count by 1. When a car leaves, the count increases by 1, allowing other cars to enter. Key points: helps in mutual exclusion and process coordination. More flexible than a Mutex for multiple resource access. Widely used in multithreading and OS scheduling. In short, a semaphore is like a traffic signal or ticket system that controls how many processes can safely use shared resources at a time. Next important short question is 4. Define deadlock. A deadlock is a situation in an operating system, OS, where two or more processes are unable to proceed because each is waiting for a resource held by the other. In other words, the processes get stuck forever and none can complete their tasks. Example. Imagine two friends crossing a narrow bridge from opposite sides. Friend A waits for friend B to move, and friend B waits for friend A. Neither can move, so they are deadlocked. Key points. Deadlock occurs when processes compete for limited resources like printers, files, or CPU. 4 necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, circular wait. Deadlocks can cause system slowdown or crash if not handled. In short, a deadlock is like a traffic jam in a computer, where processes wait forever for each other and the OS must handle it using prevention, avoidance, detection, or recovery methods. Next important short question is 5. Deadlock characterization. Deadlock characterization is the study of conditions and features that cause a deadlock in an operating system, OS. To understand deadlocks, OS experts define 4 necessary conditions, all of which must exist for a deadlock to occur. 1. Mutual exclusion. At least one resource is held exclusively by a process. 2. Hold and wait. A process is holding at least one resource and waiting for another. 3. No preemption. Resources cannot be forcibly taken away from a process. 4. Circular wait. A circular chain of 2 or more processes exists, each waiting for a resource held by the next process. Example. Imagine 3 friends sharing 3 pens. Friend A has pen 1 and waits for pen 2. Friend B has pen 2 and waits for pen 3. Friend C has pen 3 and waits for pen 1. None can write, forming a circular deadlock. Key points. Deadlock characterization helps OS designers identify, prevent, or handle deadlocks. Understanding these conditions is essential for deadlock avoidance algorithms. In short, deadlock characterization identifies the why and how of deadlocks, so the OS can implement strategies to keep processes running smoothly. Next Unit 2. Long questions. First important long question is 1. Discuss about the critical section problem. The critical section problem. In an operating system, OS, a process may need to access shared resources like memory, files, or printers. The part of the program where the process accesses shared resources is called the critical section. The critical section problem occurs when multiple processes try to access the critical section simultaneously, which can lead to data inconsistency or errors. Example. Imagine 2 students editing the same Google Doc at the same time. If both write changes simultaneously without coordination, the final document may have overwritten or lost content. The critical section problem is essentially how to allow one student at a time to make changes safely. Requirements to solve the critical section problem. The OS must ensure 3 conditions. 1. Mutual exclusion. Only one process can enter the critical section at a time. 2. Progress. If no process is in the critical section, the decision of who enters next should not be delayed unnecessarily. 3. Bounded waiting. Every process must get a fair chance to enter the critical section. No process should wait forever. Solutions. Software solutions, algorithms like Peterson's solution use shared variables to enforce mutual exclusion. Hardware solutions, special CPU instructions like test and set or compare and swap can prevent race conditions. Synchronization tools, OS provides mechanisms like Mutex locks, semaphores, and monitors to manage access to the critical section safely. Real-life analogy. Think of a single ATM machine in a bank. Only one person, process, can use it at a time, mutual exclusion. Others must wait in line, bounded waiting, and no one can skip the queue unfairly, progress. Key points. The critical section problem is fundamental to process synchronization. Proper solutions ensure data consistency, system reliability, and fairness. Without solving it, systems may face race conditions, deadlocks, or crashes. In short, the critical section problem is about coordinating multiple processes to safely access shared resources, ensuring the system works correctly, efficiently, and fairly. Next important long question is 2. Peterson's solution. Peterson's solution is a classic software-based method to solve the critical section problem for two processes. It ensures that mutual exclusion is maintained without using special hardware instructions. How it works. Each process has a flag to indicate if it wants to enter the critical section. There is also a turn variable to decide which process gets priority. A process can enter the critical section only if the other process is not interested or it is its turn to enter. Algorithm, conceptually. 1. Process sets its flag to true, it wants to enter. 2. It sets turn to the other process. 3. It waits while the other process wants to enter and it's the other process's turn. 4. Once conditions are satisfied, it enters the critical section. 5. After finishing, it sets its flag to false, allowing the other process to enter. Example, real-life analogy. Imagine two friends sharing a study room. Each puts a "I want to study" sign outside the room. If both want to enter, they check the turn indicator, like a coin flip or agreement. Only the friend whose turn it is can enter, ensuring no conflict or fight. Key points. Ensures mutual exclusion, only one process in the critical section at a time. Progress, if the critical section is free, a process does not wait unnecessarily. Bounded waiting, each process gets a fair chance, no starvation occurs. Works only for two processes, for more processes, other methods like Mutex locks or semaphores are preferred. Advantages. Simple software solution, no hardware support required. Guarantees safety and fairness for two processes. In short, Peterson's solution is a clever software method that coordinates two processes to safely share resources without conflict, using simple flags and a turn variable, making it a classic example of process synchronization. Next important long question is 3. Classic problems of synchronization. In operating systems, OS, classic synchronization problems are standard examples used to illustrate the challenges of coordinating multiple processes that share resources. These problems help understand process synchronization techniques like semaphores, mutexes, and monitors. 1. The producer-consumer problem. Scenario: a producer generates data and places it in a buffer, and a consumer removes data from the buffer. Problem: if the buffer is full, the producer must wait. If it is empty, the consumer must wait. Solution: use semaphores to synchronize access to the buffer, ensuring no data is lost or overwritten. Example: a bakery, producer, makes bread and places it on a shelf, buffer. Customers, consumers, pick bread from the shelf. If the shelf is empty or full, baker and customers wait appropriately. 2. The dining philosopher's problem. Scenario: 5 philosophers sit around a table, each needing 2 forks to eat. Problem: if each philosopher picks up one fork at the same time, a deadlock can occur. Solution: use resource hierarchy, semaphores, or monitors to avoid deadlock while allowing fair access. 3. The reader's-writer's problem. Scenario: multiple readers can read a shared file simultaneously, but writers need exclusive access. Problem: if not synchronized, writers may overwrite data while readers are reading. Solution: use semaphores to ensure mutual exclusion for writers and allow concurrent reading. Key points. These problems demonstrate race conditions, deadlocks, and resource contention. Solving them requires proper synchronization mechanisms. They are classic examples used in textbooks and exams to understand OS concepts. Real-life analogy. Think of a library. Multiple students can read books simultaneously, readers. Only one can edit a book at a time, writer. Proper rules prevent chaos and ensure fairness. In short, classic synchronization problems teach how processes coordinate safely, prevent conflicts, and avoid deadlocks, forming the foundation for real-world process synchronization solutions in operating systems. Next important long question is: 4. Write short note on monitors. Monitors. In operating systems, OS, a monitor is a high-level synchronization construct that provides a safe way for processes to access shared resources without conflicts. It is designed to solve critical section problems in a clean and structured manner. How monitors work. A monitor is like a special module or class in a program. It contains shared data, procedures, and synchronization mechanisms. Only one process can execute inside a monitor at a time, which automatically ensures mutual exclusion. Monitors also provide condition variables that allow processes to wait and signal based on certain conditions. Example. Imagine a library with one librarian, monitor, and many students, processes. Students ask the librarian to issue or return books. Only one student interacts with the librarian at a time, mutual exclusion. If a student wants a book that is currently unavailable, they wait until it is returned, condition variable. Key points. 1. Mutual exclusion, automatically enforced by the monitor. 2. Synchronization, processes can wait or signal using condition variables, avoiding race conditions. 3. Structured and safe, high-level abstraction avoids errors compared to using semaphores directly. 4. Widely used, monitors are used in modern programming languages like Java, synchronized, and C#, lock. Advantages of monitors. Simpler and cleaner than semaphores. Prevents accidental errors in process synchronization. Makes code easier to read, write, and maintain. Real-life analogy. Think of a ticket counter at a railway station. Only one person can buy a ticket at a time, mutual exclusion. If tickets are not available, the person waits until more tickets arrive, condition variable. In short, a monitor is a programming construct that ensures safe and synchronized access to shared resources. It simplifies process coordination, prevents race conditions, and provides a clean solution to the critical section problem, making OS and multithreaded programming safer and easier to manage. Next important long question is: 5. Methods for handling deadlocks. In operating systems, OS, a deadlock occurs when two or more processes are stuck forever, each waiting for resources held by the others. To manage deadlocks, OS uses different methods, each with advantages and disadvantages. 1. Deadlock prevention. This method prevents at least one of the necessary conditions for deadlock: mutual exclusion, hold and wait, no preemption, circular wait. Example: Force processes to request all resources at once, eliminates hold and wait, or allow preemption of resources if needed. 2. Deadlock avoidance. The OS analyzes resource requests before granting them to ensure the system remains in a safe state. Example, the banker's algorithm. A bank grants loans only if it can ensure that all customers can eventually be satisfied. 3. Deadlock detection and recovery. The OS allows deadlocks to occur but periodically checks for them. Once detected, it recovers by terminating or rolling back processes. Example, if two processes are deadlocked over printers, the OS may kill one process to free resources. 4. Ignoring deadlocks, ostrich algorithm. Some systems ignore deadlocks, assuming they are rare. Suitable for systems where deadlocks are infrequent or minor. Key points. Prevention and avoidance are proactive methods to stop deadlocks before they occur. Detection and recovery are reactive methods, dealing with deadlocks after they occur. Choosing a method depends on system type, resource usage, and performance requirements. Real-life analogy. Think of a traffic jam at a narrow bridge. Prevention, only one car allowed on the bridge at a time. Avoidance, let cars cross only if enough space is available for all. Detection, if jam occurs, remove a car to clear the way. Ignoring, let cars wait, assuming jams are rare. In short, deadlock handling methods are strategies that OS uses to ensure smooth process execution. By preventing, avoiding, detecting, or recovering from deadlocks, the OS keeps the system efficient, reliable, and fair. Next important long question is 6. Deadlock prevention methods. Deadlock prevention is a method used by operating systems, OS, to stop deadlocks from happening in the first place. It works by ensuring that at least one of the 4 necessary conditions for deadlock cannot occur: mutual exclusion, hold and wait, no preemption, and circular wait. Methods to prevent deadlocks. 1. Eliminate mutual exclusion. If possible, make some resources shareable instead of exclusive. Example, multiple processes can read a file simultaneously, reducing the need for exclusive access. 2. Eliminate hold and wait. Require a process to request all resources at once. This prevents a process from holding some resources while waiting for others. Example, a student asks for all textbooks needed for a project at once instead of taking them one by one. 3. Eliminate no preemption. Allow the OS to take resources away from a process if needed. Example, if a process holds a printer but is waiting for a scanner, the OS may temporarily take back the printer and give it to another process. 4. Eliminate circular wait. Impose a total ordering of resource types. Processes must request resources in a predefined order, preventing circular dependencies. Example, number all resources, printer is equal to 1, scanner is equal to 2, disk is equal to 3, and require processes to request them in increasing order only. Key points. Deadlock prevention is proactive, stopping problems before they occur. It may lead to lower resource utilization because processes may wait longer or some resources remain idle. Widely used in critical systems where deadlocks are unacceptable. Real-life analogy. Think of a single-lane bridge with multiple vehicles. Only one vehicle can cross at a time, mutual exclusion. Vehicles must wait until enough space is free before entering, hold and wait. Vehicles can reverse if needed, preemption. Vehicles enter in a fixed order based on size, circular wait prevention. In short, deadlock prevention uses rules, and constraints to ensure that the system never reaches a state where processes are stuck forever. By removing one of the deadlock conditions, the OS keeps processes running smoothly, safely, and efficiently. Next important long question is 7. Explain deadlock avoidance with an example. Deadlock avoidance. Deadlock avoidance is a method used by operating systems, OS, to allow processes to request resources but ensure that the system never enters a deadlock state. Unlike deadlock prevention, which imposes strict rules, avoidance dynamically checks if granting a resource request is safe. How deadlock avoidance works. The OS keeps track of the current resource allocation and maximum resource needs of each process. When a process requests a resource, the OS simulates granting it. If the system can still satisfy all processes eventually, it is in a safe state and the request is allowed. If granting the request leads to a potential deadlock, the process must wait. Example, banker's algorithm. Imagine a bank with 10 loanable money units and 3 customers, processes. Each customer has a maximum claim, like needing 7, 5, or 3 units. The bank grants loans only if it can guarantee that all customers can eventually get their requested loans. If granting a loan would risk leaving one customer unable to get their minimum, the bank refuses temporarily, avoiding a deadlock. Key points. 1. Safe state. System can allocate resources to processes without causing deadlock. 2. Unsafe state. Granting resources may lead to deadlock, so OS delays the request. 3. Dynamic checking. Resource allocation decisions are made at runtime. 4. More efficient than prevention. Unlike prevention, resources are not wasted unnecessarily. Real-life analogy. Think of a train network with single-track bridges. Trains, processes, can enter only if they won't block others. If allowing a train to cross could trap other trains, it waits. This prevents a deadlock traffic jam on the tracks. In short, deadlock avoidance ensures that processes get resources safely by checking each request before granting it. Techniques like the banker's algorithm keep the system in a safe state, making it efficient, fair, and free from deadlocks, while allowing maximum utilization of resources. Next important long question is 8. Deadlock detection, explain, and problem. In operating systems, OS, deadlock detection is a method to identify deadlocks after they occur. Unlike prevention or avoidance, which try to stop deadlocks, detection allows the system to enter a deadlock state but periodically checks for it and takes action to recover. How deadlock detection works. 1. The OS maintains information about resources allocated, resources requested, and available resources. 2. It periodically uses algorithms to examine resource allocation graphs or matrices to see if a cycle exists, which indicates a deadlock. 3. Once a deadlock is detected, the OS must take action to recover, such as terminating or rolling back processes. Problem. Deadlock occurs when processes wait indefinitely for resources held by each other. Example, two processes P1 and P2 each hold one printer and request the other printer simultaneously. Both are stuck waiting, forming a deadlock. The OS can detect this by checking the resource allocation graph. A cycle indicates a deadlock. Example, real-life analogy. Imagine two cars on a narrow one-lane bridge from opposite sides. Each car waits for the other to move. Both are stuck, deadlock. A traffic officer notices the jam, detection, and forces one car to reverse, recovery. Key points. 1. Detection algorithms can be resource-intensive, so they are used periodically. 2. After detection, OS uses strategies like process termination, kill one or more deadlocked processes. Resource preemption, temporarily take resources from some processes. 3. Suitable for systems where deadlocks are rare but recovery is possible. Advantages: deadlocks are allowed temporarily, so resources are utilized efficiently. Provides a mechanism to recover when deadlocks occur. In short, deadlock detection identifies stuck processes and helps the OS recover. By monitoring resource allocation and identifying cycles, the system can resolve deadlocks safely, ensuring system reliability and continuity of process execution, even if deadlocks occasionally happen. Next important long question is 9. Write a short note on recovery from deadlock. Recovery from deadlock. In operating systems, OS, recovery from deadlock is the process of resolving deadlocks after they occur so that the system can continue running normally. Unlike prevention or avoidance, which try to stop deadlocks, recovery handles the situation when processes are already stuck. Methods of recovery. 1. Process termination. The OS can terminate one or more processes involved in the deadlock. Choice of process. Terminate all deadlocked processes, simple but drastic. Terminate processes one by one until deadlock is resolved, more controlled. Example, 2 processes are stuck using 2 printers each. Killing one process frees its resources and allows the other to continue. 2. Resource preemption. The OS can take resources away temporarily from some processes and give them to others. Resources are returned later to continue execution. Example, if 2 students are waiting for the same laptop, the OS temporarily takes the laptop from one who is idle and gives it to the other to complete their work. 3. Rollback checkpoints. The OS rolls back a process to a safe state before it requested resources. The process can then retry, preventing a permanent deadlock. Example, in a bank system, if a transaction is stuck due to resource conflict, it can be rolled back to the previous checkpoint and retried. Key points. Recovery is reactive, deadlocks have already occurred. Choosing the right process for termination or preemption requires considering priority, cost, and system impact. Recovery may cause loss of work or delay, so it's used when deadlocks cannot be prevented or avoided. Real-life analogy. Think of a traffic jam at a single-lane bridge. One car reverses, process termination or preemption, to clear the jam. After clearing, traffic resumes normally. In short, recovery from deadlock restores normal system operation by terminating processes, preempting resources, or rolling back operations. While it may cause temporary inconvenience or loss, it ensures the system continues to function safely and efficiently, preventing permanent standstills.